Supposedly, this is recording. Okay.
Are you recording just you or us?
I'm only recording, well, okay, video-wise, why do you want to know? Okay, so this is recording audio, so mainly going to capture what I say, or you guys if you're loud enough. Don't get any ideas. And video-wise, just my screen. Yeah. Okay. All right. So as I type, maybe a little delay as understanding my LaTeX commands, but it'll all show up, and at least it'll be a whole lot more legible than my writing on the board, as some of you can attest to. Okay. All right. All right. So I just want to point some things out about how to go about this class in a way to try to at least reduce your suffering. Okay. But the thing is, I know for a fact, based on prior experience, because I say these things all the time, every class, that probably more than half of you won't heed them. But hey, gotta try. Okay, so I can make this bigger. Let's see.
Can I ask what you're using right now?
It's called a Bacoma Tech Word is the product.
Making latex so much easier.
Oh yeah, definitely. Unfortunately, this product is not free.
It's really nice.
Yeah.
Have you used LibreSoft with the LaTeX extension?
LibreSoft? No, I haven't. Is it a similar thing where it goes on the fly, or?
Yeah, it has a LaTeX extension. I just haven't used it.
Oh, okay. Yeah, because when I was trying other things in this class, I got frustrated with it. I want to be able to do LaTeX right here in class. I just Googled WYSIWYG LaTeX, like for what you see is what you get, and this is what came up. Now, you will hear me grumble about it because now and then it messes up, but generally, yes, it's a great thing to have.
Have you ever used it?
TechSoft? Not familiar with that either, but okay. Okay, can zoom in, that's good. Can this be read down at the coast? Or does it need to be?
We can read. We can't read the LaTeX, but we can read.
Oh, yeah, just this top part is all I care about.
Yes, I read it.
Okay, good. All right. Now, all right. So when I say this is not a calculus course, it's kind of a loaded statement. But what I mean by that is, I feel like Dr. Schroeder does bullet points in faculty meetings, but oh well. Okay, so so what does that actually mean? All right, because the way math classes are normally set up, depending on the class, it could be like, stating a theorem, maybe proving a theorem, doing some examples of problem-solving techniques, and so forth. And in that sense, this class is not really any different from any of those, but this comment really applies not just to 460, but to upper-level classes in general. It's not like Calculus 1 or 2, where I can fit in literally a zillion examples, whatever you define a zillion to be, in a single class period. And as you move up from lower level to upper level courses, that becomes less and less true. For example, when I teach Cal 4, it's very easy for one example, like working out a triple integral or something, to take up the whole class time. It's awful. And by the time we get to Math 460, emphasis on the 4, it gets even worse. I do try to illustrate all the concepts I present. I don't expect you guys to grasp it in the abstract right away or anything like that. But again, time is limited. But the thing is, because you're at this level, that's the real point here. There's an expectation that you have higher powers of abstraction than someone who is taking Cal 1 to be able to apply what is being taught. Now, the next point, so I want to make sure there's not unrealistic expectations about that. Another item is, okay. I have students tell me this every semester in one class or another. They'll come to me, they're having difficulty, and they say, I feel like I'm the only one who's not getting it. And often that statement is based on their observation that they sitting there themselves are confused, but they don't see anyone asking questions. So they feel like, well, they must all understand it then, and I don't. So let me tell you the truth on this next bullet point. Okay. All right. And here's why. Okay. The reason why that's true is it's really unrealistic. Well, sorry for my spelling. It's not like Microsoft Word auto-corrects it. Because when you're sitting in a Cal 1 class or something that lower level, or like linear algebra, professors working things out and think, okay, yep, I'm getting this, hopefully. And again, as you go to higher level classes, that doesn't really apply anymore. You may get it to a certain point while you're sitting there in class. Don't expect to get everything. It's going to take additional time outside of class to really get it, and it may come while you're working through problems, for instance. That's why I encourage actually looking at the book, because when I was a student, I did things the wrong way too, where I'd be assigned problems from a book, and that's the only part of the book I would look at. And over time, I realized, there's useful information prior to that. And actually, I tend to rely on whatever book I was using, even if it wasn't great, more heavily than what the professor was saying. And maybe it's because I had trouble paying attention. I don't know. But there's what I've observed. I've been here for 10 years. What I've observed is that students seem to feel like pretty much their only time to learn material is, number one, while that sitting in class for those 50 or 75 or 90 minutes or whatever the administration subjects us to. But also grasping it by functioning in a passive way, which I discovered the hard way last time I taught this class when I tried a bunch of active learning techniques. The students practically revolted. And because it wasn't what they're used to. As someone I work with has often said, math is not a spectator sport. You're only going to be able to get to a certain point from seeing me do things up here. So that's why the book was written in such a way as to encourage working with things in a hands-on manner, because that's really what's necessary to understand it. Okay. Next bit of advice. Okay. Really tired of this one. I've taught at 4 universities, and compared to the other 3, students at USM are, with some exceptions, but are really awful at asking for help. Like, apparently they would rather stab themselves with a fork than do it. I don't give answers. A lot of these problems get pretty involved. So what I can do is try to move you forward a little bit and then set you up to take the next step yourself. And the thing is, when I'm working with a student, it doesn't matter whether it's in class or students I do research with, there may be more of a need to depend on me at the beginning to, like, if you think of your intellectual growth from all of your classes as like building a house. If you come to me for help, I'm not taking over the building of a house. It cannot work that way. I can give you tools to continue building it yourself. That's the way this works. So I do my best to make myself very available to students, whether it's in my office, here, or over email, etc. And those students who know me from prior classes are aware of this. That I'm basically on call for you guys, all of you. And besides, I only sleep 4.5 hours a night anyway. So, and so many times a student will tell me, "Oh, I didn't want to bug you," and I'll apologize on behalf of my colleagues who should have been one apologizing, who, if it made any of you feel bad for asking a question or bugging them. Okay. So, all right. So I just want to be very clear on the record for how I feel about that. Whether that is consistent with what you've observed, experienced in other classes or not, this is my class now. Okay. Okay. Now, to set the stage for overview of numerical analysis. Okay, we have 37 minutes left. Okay. Okay. So, all right. Like I said, I've been here for 10 years. Okay, so I double majored in math and computer science. So for numerical analysis, those majors are extremely useful. Okay, and okay. Oh, also, might as well date myself. I think most of you weren't even born then, right? Yeah. Okay. Okay. All right. And my PhD was not in math. Not that either. It was an interdisciplinary program with a very long name that was usually abbreviated. Okay. Because I love both math and computer science as much as an undergrad, I didn't want to have to choose between them, and then I found out I didn't have to. Okay. And because I took my first numerical analysis course, it was 31 years ago, 1988. And that's been my favorite field of math ever since. Okay. Whoops. Yeah, this is one of those strange things about this Bacoma tech word editor, that it puts those strange question marks in there. I have no idea why. And other strange behavior. So you'll hear me grumble about that. All right, so I specialize in numerical methods for partial differential equations. That is the subject of one of our other upper level courses, Math 417, that's taught every spring. So this field of numerical analysis, which is also known as scientific computing, is one of the fastest growing and also best employing areas of math, even though the students at your level may not necessarily be aware of it, because you think of math as calculus and modern algebra and proofs from hell. things like that. But here's another side of it, and I really wish that, as an institution or as a community, that we do more to make students aware of it earlier. Because so many of the smartest high school kids, they come into college all wanting to be doctors because their parents think that that's the only worthwhile career to pursue. But there are 2 of the nation's 5 unclassified supercomputing centers are located in Mississippi. There's NASA Stennis Space Center, and that's where I was actually working last summer. I was a faculty research fellow at the Naval Research Lab, and it's amazing how much research you can get done when you don't have students underfoot and you're locked in an office for 10 days. Well, not locked, but but yeah, I shut myself in there. Also the Army Corps of Engineers Research and Development Center, which is just up the road the other way in Vicksburg. So there's some very interesting career options, even locally, that people may not be aware of. And I will also point out they're hiring. One in Vicksburg has already hired 3 of my former graduate students, and they're prepared to take more. So in particular at Naval Research Lab, I was working on in their acoustics branch, so modeling wave propagation in the ocean. Yes.
Is that second one the one from Mississippi State that they put out per hour?
Did they what?
The supercomputer lab?
I know we have some connection to Mississippi State, so that probably is the case. Yeah. Actually, one of my former master's students works there as a researcher, and she's getting her PhD from Mississippi State, so she telecommutes up there. So, yeah, that probably is the case. Okay. Actually, our own computational science PhD program was established like 15 years ago or so, to serve researchers from Stennis. Unfortunately, that market has dried up. Okay. Okay. So very good idea of where I'm coming from. That I enjoy coding and I enjoy proving things. I actually chose math over computer science, believe it or not, because I found it more challenging. In other words, I got greater satisfaction from working things out in math than in computer science. Now, if I had known a computer science professors got paid more, I may have thought differently. But again, I do a lot of things that are not money making. So, okay. Now, so what is this numerical analysis thingy? Okay. Now, I gave a one-line description before. Solving math problems by computer, and that means there's a distinction to be drawn between analytical versus numerical methods. So I'm going to give a few examples of analytical methods. Okay. Ones that you have already used. When you were working on integrals in Cal 2, you learned several integration rules, and you had to recognize, for a given integral, which integration technique was the best to use. Should you use a substitution? Should you use integration by parts or partial fractions? Now, there is software that implements those kind of approaches, but that's not playing to a computer's strengths. Computers do arithmetic best. So artificial intelligence still has a ways to go. And then at some point, they'll come up with Skynet and kill us all. But another example, from linear algebra. If you're given a system of equations, to solve linear equations. So you perform row operations to reduce to row echelon form. Hopefully some of that rings a bell. Or your linear algebra professor would be very disheartened. And so that's an approach that you can carry out by hand. And then one more. Suppose you have a differential equation of like something like this, like y double prime plus, well, I'll go into math mode here. Y double prime plus py prime plus qy is equal to r. Okay. Oh. Okay, so something of this form. And one of the methods that is taught in Math 285, method of undetermined coefficients. Now, not all of you may have taken that class. It's not a prerequisite. But chances are you will take it later because it's one of our electives, but who wouldn't choose that one? It's probably the easiest one. Okay, so you might think, okay, in your other classes you've learned these methods for solving these problems, so why do we need anything else? If we can develop software for computers to carry out these same techniques, why do we need to do anything different? Why do we need a separate area of math to explore techniques for computers to solve these same kind of problems? And that's what I'm going to explain now. Okay. Actually, I'm going to put this on a new page, just so you can see everything side by side. Okay. All right. So, oh, not numerical. Well, both kinds of methods have their limitations, but I want to focus on the competition first. Okay. So, and I'll go through these points one by one. First, I was talking about an integral. And there are many integrals that I can give you that, if you remember your Cal 2 well enough, you'd be able to work out. Although, it's probably been a couple of years, so you may have forgotten it already. But here's an integral. Okay. Actually, I'm going to make that a little bigger. Okay. E to the minus x squared. Now, if I gave you the integral of e to the x, or e to the minus x, that's easy. E to the x is its own integral, or if it's e to the minus x, it would be minus e to the minus x. But once you square it, can't do it. And I don't mean it'd be really hard to do using techniques like you'll learn in Cal 2. I mean it is literally impossible, meaning it has actually been proven it is impossible. I don't know how you prove that a problem is impossible. I haven't looked up a proof of this, but it has been proven. Can't be done. But, and I think, well, who cares? Well, actually, ask a statistician. They care about this one a lot. This is a Gaussian function. Gaussian functions are important in many areas of math, not just statistics, but also differential equations and so forth. So it's really unfortunate that we don't have a nice formula for this. Analytical methods have their limitations. System linear equations using Gaussian elimination. What if you have a billion equations? And I'm not exaggerating. These supercomputing facilities, they really do need to solve problems with this many unknowns. They don't play around. And tactically, something like Gaussian elimination, these row operations can be used, but there are other options that are a whole lot more practical, ones you would not dream of using for a problem you're solving by hand. But like if you, in Math 326, in your linear algebra, if a professor gives you a system of 5 equations and 5 unknowns on a test, they probably could labeled sadistic. Once problems become large scale, and not even that large, you really need a computer to do the work. And there's going to be issues involved as we get into, especially in Chapter 2. for when a computer's doing the work, why things go awry. And I'll tell a story about that today also. Okay, 24 minutes left. Doing good. And method of undetermined coefficients. What about a slightly different I'll fill in a specific coefficient. Like, if I assume that P and Q are constants, you know how to solve that. That's something you learned in Math 285. But if I make a variable coefficient, maybe in certain special cases, it can be solved. But here I make a variable coefficient. I fill in an e to the x there instead of a constant p. Everything you learn in 285 or even a more advanced class, not going to help you. You must solve it numerically. Now, 460 is the first course in a two-course sequence. There's 460 now and 461 in the spring. So certain kinds of problems we'll deal with in the spring if you are masochistic enough to go that far. I'm guessing most of you won't just because of your degree requirements, but you're welcome to join. Linear systems, differential equations will come up in the spring. Certain other problems will be covered in the fall. Another one that will come up this semester, you should know how to solve this equation. Let's say cosine x is equal to cosine x is equal to 1/2. All right, let's put you guys on the spot. Can anyone give me a solution to this equation? What?
Is it 3 pi over 2?
No, cosine of 3 pi over 2 is 0.
No, that is cosine pi over 2.
Cosine pi over 2 is also 0.
Pi over 3?
It's 0. I spotted it. Pi over
60.
Pi over 3? Pi over 3?
What?
Pi over 3?
Yes.
In what part of it?
Yes, 60 degrees or pi over 3 is a solution. Of course, there are infinitely many solutions. Okay, so that's one you know analytically, like by learning your angles. Let me change the equation a little bit. I just throw in an x in front of a cosine x. Now you're out of luck. Can't do anything. Yes. Or certain numerical methods that will be covered towards the end of this semester. Now the thing is, like I said, both analytical and numerical methods have their pros and cons. Okay, so for analytical methods, for pro, you get the exact answer for whatever problems you're solving, like that pi over 3 in that case. Con is there's only a limited selection of problems you can apply analytical techniques to. In Cal 2, you learned how to handle certain integrals, but it would be trivial to come up with an integral that doesn't fall into any of those baskets. Then what are you going to do? Whereas for numerical methods, and you can have there are techniques for evaluating integrals that we'll see this semester, and you can really try them on anything. And in most cases have some hope of getting an accurate answer. The con is that is not the exact answer. It's going to be an approximation. Now, it may be a highly accurate approximation where the error is so small that it's negligible, like preferably like 10 to the minus 15 or something like that. And in many cases, you might not even need that. So this is, and much of the time, this is not really any kind of deal breaker. In real applications, you don't necessarily need an exact answer most of the time. But of course, we always want that if we can get it. Okay. And the other thing is, what about efficiency? Because of computing power is growing all the time. So everything is computers can perform so many megaflops or teraflops these days, so they can solve these problems a whole lot more than even the easy ones that we can analytically, and with more than sufficient accuracy. Okay, and the thing is, as computing power grows, our expectations of what computers could do is only going to grow. Like that's why we expect better animation in our movies. Okay. Now, so when it comes to numerical methods, there are certain properties we want them to have. Or there's three main criteria. Bless you. We want them to satisfy. Okay. First, this one seems kind of obvious, but anyway. Of course, we want accuracy from them. But the meaning of an accurate answer varies from application to application. Sometimes you may not really require high accuracy. Maybe being accurate to within 1%, so error being about 0.01, is more than sufficient. And other times you want several decimal places correct. Why? Because maybe the problem you're solving in the first place has some uncertainty in it. So even if you could solve it exactly, that wouldn't really gain you anything. So it's important to take that kind of input error into account. And error analysis is going to be one of the major topics of this course. So in terms of the error in the input and the error in the output and how they relate to one another. We certainly want we certainly want these methods to be efficient, but we don't want to sacrifice accuracy either. Sometimes a method can be made really fast, but could run afoul of one of the other criteria, so we have to be wary of that. And not just time, but also space. What I mean by space is storage space. If you have an algorithm that requires too much memory, even if it might be quite accurate and efficient in terms of fewer arithmetic operations, if it uses up your storage, then it's still no good. So try to minimize communication of data, movement of data in memory is also an important criterion. Okay, and one that this is the one that really comes back to haunt you if you forget about it. Robust. In other words, reliable. We don't want a method that works very well for certain problems and fails completely on others. Mathematical software that does that would not be used by anybody because you have to know what to expect. You have to be able to trust the answer that you get. And I'll flesh it out more when we get to Chapter 2, but basically a small change in the input should not cause a large change in the output. But unfortunately, certain problems do have this unfortunate property, where a tiny change in the input could lead to a large change in the output, and that's a property of a problem you're solving, not the method you're using to solve it. And then sometimes the problem itself can be fine, but the algorithm could be bad. So there's multiple things to look at here that we need to be aware of. Okay, so these are the criteria that we'll look at with each type of numerical method that we encounter. Okay, now real quick, I'm running short on time, but okay, so just a quick overview of what kind of things are we going to see this semester. Starting with MATLAB. In Chapter 1, So I'll be using the next several classes to go through a MATLAB tutorial so that you can be up to speed, get your programming brains working. I know some of you have more programming experience than others. I don't assume programming expertise. We're going to go from the ground up. So anyone who has MATLAB experience already is going to be super bored. And I'm sorry, not sorry. Okay, next, error analysis, including computer arithmetic. So every arithmetic operation, and no, I'm not mispronouncing arithmetic. Arithmetic is a noun. Arithmetic is the adjective. Arithmetic operation introduces some error. An error is generally going to be very small, but it can accumulate. So we have to be careful about that. Certain operations are riskier than others. And there's other and also the studying of how does input error relate to output error. Can it be magnified? For what sorts of problems can it be magnified? So this is chapter 2. Then we skip ahead some. Chapter 7, Polynomial Interpolation. One problem that you learned to solve a long time ago, I just taught in college algebra, is given 2 points, find the equation of a line that passes through those 2 points. Well, now we take that to a higher degree. If 2 points prescribe a line, 3 points determine a parabola, 4 points determine a cubic, and so on. So given a collection of points, like n plus 1 points, you can find a unique polynomial of degree n that passes through those exactly. What are efficient ways of constructing those polynomials? So I'll show you how to do that, make a nice party trick. Okay. Next, probably my favorite chapter. So, calculus by computer. How to approximate derivatives and integrals without having to use all those fancy integration and differentiation rules in chapter 9. And some of these techniques are extremely sophisticated, very efficient. Okay. And then the last chapter will be covered this semester, nonlinear equations, like the one I showed earlier about x cosine x equal to 1/2. So in chapter 10, we'll learn iterative methods for solving nonlinear equations. So something that you can't solve using algebraic manipulations, you can use these methods, or a computer can, to do so very efficiently. Okay. So, and then if you stick around for 461, then chapters, well, certainly, I guess 3, 5, 12, and 13 probably will be covered then. So we won't see the whole book, but a good chunk of it. You won't see the rest, become a grad student. So, okay, some of you have. Okay, so in the last 10 minutes, what I want to close with is okay. All right. So, how many times have you heard, or maybe even said, that math, especially upper level math, doesn't have real world relevance? Yeah. Yeah. So, so I can show just how real this can get. 1991 Gulf War. So what was going on during that war, among other things, was so American Patriot missiles were launched to intercept Iraqi Scud missiles. Now, how's that done? What you do is you estimate the velocity, which would be roughly so like difference in position divided by difference in time. So that way you could get an idea of a Scud missile trajectory and figure out where to fire a Patriot missile to intercept it. So positions would be vectors, but you can think of this as being x, y, and z to get the x, y, and z components of the velocity vector. So what happened was, usually this worked quite well. The successful interceptions. But one time an interception was badly missed. So follow the same procedure, estimate the trajectory, fire a Patriot missile, missed by a mile, and Scud got through, and tragically 28 American troops lost their lives. So the government performed an investigation. How could this have happened? If it had worked so many other times, why would it fail this time? That just seemed mind-boggling. And the reason why comes from numerical analysis. Okay. Okay. So what was the culprit? Something that you would think would be no problem at all. And that's why these things are hard to find and diagnose. That the subtraction of two time values was the problem. Because what happens is, as you start tracking Scud missiles and getting in position and noting a time to track them, you're subtracting time values. And at first, the values T1 and T2 are small. So everything's fine. But as you leave your equipment running, tracking more and more Scud missiles, these numbers get larger and larger. You're subtracting larger numbers, but the difference between them, chances are, is still small. So what happens is, subtraction is inaccurate when the difference of two values is much less than the values themselves that you're subtracting. So in other words, two relatively large numbers that are really close together. Now this symbol here, this double less than sign, this is shorthand for much less than. That's not quantified, of course. So when this difference is much smaller than numbers being subtracted, it's inaccurate. I won't get into the reason why today. I will cover that in Chapter 2. I want to leave something for then. So this was inaccurate. It threw off the velocity estimate. So that's why Patriot missile took the wrong path. So the next question is, now that they figured out that that was a problem, how do you handle it so it doesn't happen again? The solution was actually surprisingly simple, because if this error was a result of these numbers being large, when it's fine if they're small, what you do is you prevent them from getting large. And how do you do that? Every so often they restarted their tracking. So that set T1 time value back to 0. And they determined that within this bound of 8 hours, whatever error was incurred from the subtraction, if these were less than, like how many seconds in 8 hours or whatever units they were using, that level of error was acceptable, that there would still be a successful interception. So these kind of problems are quite insidious, because it's something that you're doing something that you feel like it should work, and the thing is, in most of the time it does, until it doesn't. And so one of the key aspects of numerical analysis is to try to detect these things as algorithms are being designed before they're put into practice. Okay, I hear the noises of packing up. That can wait till 8 o'clock, so I find that annoying. Now today doesn't really matter, because I actually have come to the end of my spiel, but one of these days I'm going to be working something out, and I'll hear about rustling, and it's like, stop it! So, you've been warned. Okay, so, all right, so things I need to do. Okay, So make sure that everyone has a link to Chapter 1, which is something else I was supposed to send out. MATLAB. Did I ever send it? Oh,
That was already
Those
sent.
people who got
send it again. And I'll resend all the info from the first email to make sure that people who've added a class recently have it. If I didn't include MATLAB, I'll just include it again. Oh yeah. So any links of interest I'll put on the site also. Okay, and this screen recording of all my rants will be posted sometime tomorrow. And this document here that I've been typing out, I will post that too. Okay, so that's it for tonight. Wow, it's dark. Yay. So, until Tuesday, enjoy Labor Day weekend.